All right. Welcome to the video portion. We're going to actually start talking about distributions of samples. And I've talked before. How do we find population mean if we can't pull the entire population? Well, there's the population. And somewhere in here is mu. Well, how do you find mu? I can't just go and say, hey, right there, I'm going to pull that sample because I know mu's there. Well, that's not exactly how it works. So what do we do? Well, it's not letting me change colors. All right. So how do we find it? Well, I do it through sampling, and I do a sample mean. There's one. Well, it's fading on me. All right, try again. There's one, and it will have a mean. And the sampling mean is the X bar. So I'll have one. Then I pull another one. There's another mean. Then I pull another one, and there'll be a mean in it. Then I'll pull another. And I'll pull another one. And then we have a process where we take all the means, and we'll say there's 100 of them. And I will find the mean of the means. Well, this is a slightly different process than what you would think it is. So for the intro lesson, we call it the mean of the means is the mean. All right. So the mean is the mean. But it's the standard deviation, because remember when we talked before that what happens as I start tweaking the bell curve. Well, we talked about when the mean, how it moves it around left, right, and all such. But what happens when I want to zoom, want to arrow in and shrink down and target in? I start to what? The standard deviation needs to is it increase? No. It needs to what? Decrease. The smaller the standard deviation, the tighter the curve. So I want to get a narrow one. Well, this is what we are going to talk about, is how do I get a smaller standard deviation? Because again, if I can't pull a population mean, how do I get a population standard deviation? Well, what we're going to find is the sample standard deviation, except we're not going to no longer call it a sample standard deviation. It's the deviation of the means. All right. And what its official title is, it's the standard error of the means. Now, what I'm going to tell you, if it looks like a duck, acts like a duck, quacks like a duck, it must be a goose. The standard error, actually, we call it a standard error, but guess what? It really does look, act like a standard deviation, except it's the error of the means. So look at the symbol. We even give it the same symbol as a standard deviation, but it has its own formula. We're going to take the population standard deviation and divide by the square root of the sample. Okay, that's the formula. That should start to embed. Now, when do you know when they are talking when to do that? It's when you start to do random samplings, and then they tell you about the population, and they said, now let's take a random sample of. This is going to be your flag going forward that, hey, look, we need to tweak the standard deviation. All right. So with that being said, before we can do this, we have two criterias that must be met. And I do mean they must be met. You've got a text message. Sorry about that. You guys just got to hear my cell phone go off. We have two criteria. And this is before we can move forward. Criteria number one. You must have a random sample. So how do we know when they've done random sampling? One, they have to declare it. Yeah, we really do have to declare these things. Otherwise, we can have people call our studies insignificant, whatever. I mean, but they will call us on it. And we have to show how it was random. If we're doing a big study, we do have to show that how we did it and made sure that was random. In your problems, it's going to state it's random. Or watch who did the poll. If the poll, the information we're giving to you is done by like the major ones, like a Pew Repolls, I can't think of some of these. I'm tired right now, sorry. But we've got some national and international research institutes that run the polls, and they have the criteria in place. So when you're looking at information being given to you for your homework and such, if it doesn't state, look to see if they cited where they got the information. And then from there, you can say, yeah, we're going to assume it's random because. But don't let that stop you from, be on the alert, because heaven forbid I throw you something that, may not be random. Two, must be independent well, if I could write with my finger. Yes, it's a cute little scroll at the bottom of the page. It must be independent without replacement. How do we test for that? Yes, we have a test. The sample size must be smaller than 5% of the population. That is the test. You will get tired of that test. Now, if I said that I have 250 people in my study, and I'm saying I'm sitting here and I'm studying smokers in the United States, I can pretty well make that assumption that 250 is less than 5% of all smokers. Sometimes it's a like, think about that. It's a logical deduction that, yeah, the sample, what we're pulling, their description, is something like that. Yeah, we are less than 5%. Okay, so let's turn the page. When you turn the page, we have two examples of a population size. The first one, well, they both have 500. We have a population of 500. And the first question is a sample of 50 too big, too small? Well, I can plug that, I'm going to plug it into the formula and I can check. Or we know that has to be less than 5% of the population. So let's see, what is 5% of a population of 500? So 5% of 500 is 25. So I have to have a sample size of less than 25. Looking at the first one, A, does it meet? It's saying I have a sample size of 50. Answer is no, because that's actually 10% of the population. So A, no, it's too big. But looking at B, my sample size is 20. My sample size of 20, isn't that less than 25? So B, it's a good to go. All right. Now, looking at example 2. Example 1 was just kind of getting you familiar with the formula. Sample 2 is getting you familiar with the other formula. 1 says find the mean of X bar, the mean of the means. Well, remember what I told you, the mean is the mean, which is 100. That one's the easy one. But we want to also find that. And that's the formula of what? The standard deviation over the square root of n. Well, the standard deviation is what? 18 over the square root of 16, and the square root of 16 is 4. So 18 divided by 4 is what? 4.5? So you can see by taking into account of the sample size, the population standard deviation was 18, but when I took a sampling, I shrunk the standard deviation, or the sampling of errors. Remember, again, if it looks like a duck, quacks like a duck, must be a duck. The sampling of errors, the error of the means, whatever, how you can remember it, is 4.5. So we really took a bell curve that looked like this to a bell curve that looked like that. And that's what we want to do. All right. So looking at this, example 3. Example 3 is calculator. And Mr. Toby, now's the time to teach them how to do z-scores and such on their calculator. All right. So at this point, I'm going to let you go ahead and take the wheel, pause it, go ahead and do an example 3 like we talked about. And when you get to the central limit theorem, bring the video back on. But I'm going to keep going now. I'll give you a moment to pause. Okay, now that you're back and you went through that example 3, let's talk about the central limit theorem. The central limit theorem I've been kind of talking about say if you give me a big enough sample, you heard me say it about regression lines. I said, give me a big enough sample and I can draw a line through it. Well, the same thing plays with bell curves. And I want you to look at figure 10. So, for any reason, as we increase the size of the sample, for whatever reason, our bell curve tends to what we call normalize. Meaning, if you look at figure 10A, I would say that that is very skewed right, correct? So I draw a curve on that, it's going to look like that. Look at that histogram. It's on the bottom of page 3. But look on the next page, on page 4, at B. I increased the sampling. And you see how the curve shifted. It shifted to the right. In sample C, I added, increased the sample size again, and it shifted more to the right, and it's starting to skewing is starting to go away. So I guess that's a sample size of 10, not 30, and that's hard to read. So I went from a sample size of 4 to a sampling of 10. Now I'm going to do a sampling of 25, and that's version D. And by that sampling, looky there, I went from a population that was skewed to a sampling that is normally distributed. And then I've now met the central limit theorem and I've got normalized data. This is one of the tricks that we can pull when we have data that is skewed. We increase the size of the sampling. Think along the lines of the law of large numbers. It's not really the central limit theorem, but it's still along the same ideology. The bigger the sample, we can start to normalize. So, what does it mean? If we don't know the population, it means sometimes we don't know if the population is normal or not. So, we've discovered that when we hit about 30 on our sampling, and preferably we like bigger than 30, we know that our sampling now has become normalized. It's evened out. It no longer looks like A. It now looks like D, where it has normaled out. But by increasing the sample size, we move from something that's skewed to something normalized. Okay? So we can make assumptions when we hear certain things. Well, what can we assume about the population? Well, I can make assumptions on that. If I have a population of a sampling of 16 that is normally distributed, which is actually example 4C is what I'm talking about, what assumption based on the central limit theorem can I make about the population? Well, if I'm saying that 16 is normal, I have to, and I say I can use it, that must mean the population itself was normal. This is the reverse of the central limit theorem. All right. So looking at example 4, it says answer the following. Well, if you look at that, it says what's the sample mean? Well, again, we're just reading the bell curve. And the bell, what is it? It is what? 79. It's the middle number. You guys did this just for me last week. So what is the value of the standard error? It reads the same way with a normalized curve. What's the difference between 79 and 82? It's still 1 standard deviation, 2 standard deviations, except it's no longer what? Standard deviations, it's standardized errors. Looks like a duck, quacks like a duck. It falls the same way. 1 deviation out, 2 deviations out, 3 deviations out, 3 deviations out. We have 99.7% of the data. See what I'm saying? It really is the same thing, except when we start tweaking it and shrinking the standard deviation by using the sample size to shrink it. This is when we call it the sample error, the sampling error means. Right? So that is 5, page 5. So looking at D, I'm going to go ahead and let Mr. Toby take it from there. And I will see you guys back next on Wednesday. I'm here in Indianapolis until Tuesday night. I should be back in town Tuesday night, probably about 10 o'clock. And then I'll be there on the prison on Thursday. So go ahead and Toby, take this time now to finish out this packet. All right. And also, any questions or anything, use this, guys, as a study guide. Don't you dare take off on me. This is a kind of a day for you to work and get some questions, like an extra study session. So, Mr. Toby, I can't thank you enough. I will see you on Thursday.